Alright, I think it's a good time to get started. So, for the next couple days, what I'm going to be streaming is just a little bit of fun, not one of my main projects, but a participation in the Handmade Network Visibility Jam. Let me actually pull that up for you. Handmade Network. So if you go over to Handmade Network, they got a new website over there, by the way. It's really cool. Like, it used to be very different. Now you come in here and you can go try find projects, but like starts with this like news feed kind of thing, and so you can you link straight to Visibility Jam, which is just really good like design. It's a good design for like the flow of finding what I'm looking for. That like relevant stuff is just right here, looking good at the front. Anyway. So this was over the weekend, Friday, Saturday, and Sunday, but I didn't want to stream and work over the weekend. I've been working hard for the last few weeks, maybe a full couple months actually. So it is high time I took a low pressure week and took the weekend off. So I'm going to do it Monday, Tuesday, Wednesday instead. So we're technically outside of the time range for the Visibility Jam, but that's what I'm doing. And in the spirit of not doing it right, I'm also going to do something a little different from what a lot of other folks have done. If we go here, we can see, well, now there's new stuff here, but like there's a lot of like BYP has some visualizations of the I forget the name of this algorithm, but the one for finding loops in a linked list where you have two pointers moving ahead. So that's cool. And this is an animated visualization, which is cool. Yeah, it's neat. Looks like visualizing a oh, what is this? This looks like a regular expression visualizer, but then what's down here at the bottom is some kind of, it says union members. What have you? That looks like a regular expression on top, and that looks like a visualization for a regular expression. BYP says it's the Floyd and Brent algorithm. Okay, cool. Yeah, I'm never going to remember that name, but it's a cool algorithm. You, like, step ahead the pointers at different rates, right? Like, one of them goes two at a time. Tortoise and hare algorithm. I think that's what I've heard before, but I didn't remember that either. A little easier to remember, though. Yeah, I'm not sure what Ben did here, because there's like memory stuff down here, union members. Wire height, text input data. Maybe this is the visualization for this? I don't know. I'll have to read more about it. It looks cool. Yeah, this is definitely like memory visualization stuff. Interesting. Well, anyways, point is, I'm going to do it wrong. I'm going to do the Visibility Jam too. But while everyone else, this is something I think is very common in like handmade network culture stuff, which is that we tend to work on software that either is games or it is software about computing stuff. We do computer work to explore and understand algorithms and data structures and low-level computer organization and computery stuff. It's very meta. It's like computer stuff about computers. I'm going to do computer stuff about math. I want to visualize math stuff. And so it's not quite the same vibe, but I think it's important to like, you know, explore on the boundary of the culture. So while we're visualizing stuff, we're going to visualize stuff like a differential equation today, one or two variable differential equation. So we're going to get into this. So where I'm going to start is, I don't know if you've seen it, but I announced the membership system for my website last week. And I can show you what that looks like here, but let's get ready. So there's flow effect, right? So I have this thing called the flow effect in my code base that looks like this right now. It's a program that runs and it just generates this effect. And if we let it play for, you know, the next 8 minutes, it kind of like evolves over time. And it probably looks crazy over video compression. But you'll see over here in my membership system, or in the announcement video, that effect was the background to this video here, which looks real crazy. Where's the there we go. But anyway, point is, so I made this for the announcement video, and if you haven't seen that, go check it out, by the way. But I would like to now kind of retrofit what I made for the purpose of animating differential equation visualizer. Because I got this flow effect thing, and the first step I'm going to need to do is to just get my head around how all of this was working. I remember feeling like it was nice, but that there was definitely some design mistakes that I made as I was hacking it together for the first time. So we're starting off with a refactor pass, and it's a refactor pass where we don't have the details of the, during a refactor you have like the before state of the code and the after state of the code. And we don't have the details about how the before state works loaded into the head yet. So that's the first thing we need to do, is load up everything we can about the before state of the code into our working model in our heads. And if we understand how it's working, then we can make a plan for what will be, we'll know how we want to take the code and the algorithms, the rendering, all of that, and rearrange it to be more reusable, be a little nicer to work with in the future. And then that's our plan, and then we can execute that plan. So that's what I want to do first thing first, is just take the flow effect that I already have and refactor it to something that we can use in more general ways, so it won't be just tied in with this little video background renderer thing that I did. So let's do that. We need to start by reading through what I did. So this chunk here is not super relevant. This is just how I submit geometry to my renderer. Geometry comes in the form of a point and a 4-coordinate color right now. So like each triangle, it's just 3 points makes up a triangle. 3 of these makes a triangle, which can be any color. The triangle can have a gradient on it. And then I make up a big batch of those and submit the whole thing. The thing that controls the particle effect is this stuff here, plus this part here controls the stuff that is specific to the effect from the video, right? So this is the particle system essentially, and then this is the root data structure of the animation. My particle structure has 3 states it can be in. So a particle can be ready, moving, or stopping. And we can see that each particle has a state of its own. So the states are per particle. And then each particle has a position on the screen, a trail of positions. And that trail has... So trail count tells us the size of this buffer of points. And head and end, which are a weird pair of names. Head is where... Well, we're going to have to actually read a little bit more carefully here. It looks like whenever we add in a new position, or whenever, yeah, so we submit a delta to the existing position. So it modifies its existing position, and then it writes the new position into the trail. And then to do that, it's incrementing the trailhead, and it loops around. So the trailhead is whichever position we've most recently written to. When we go to write a new position, we're incrementing the head by 1, and then we're writing to that new position. So if we ever want to see our current position, we actually don't need P necessarily. We could be doing something. We need it for the start position, I guess. No, we don't even need that. So in theory, we could have done all of this without the P variable, because we would have just read the P variable out of the head of the trail and then incremented the trail and then updated the position and put the new position in, right? But the P is probably useful for another reason that we'll get to as we're exploring here, I think. By the way, questions are welcome. I didn't say this at the beginning. But if you're following along and you have questions about this or about any of the Mr. Fourth Lab stuff, feel free to ask. I'd love to be able to make sure other people who are hanging out can follow along and understand what I'm working on as well. Okay, so the trail end is always one after the trail head, I guess. Which is kind of funny. So the trail end is the last. We have this buffer, and we're writing new things into the buffer over time. And wherever we've written most recently, if we go backwards from there, we see the trail, and then it wants to be able to loop around. And so the end tells us the index of the last spot that is not. Yeah, it tells us where the trail ends. That's why it's called trail end. That makes sense. I guess I can see why I didn't call it trail tail, because it's just too strange. Like, head and tail would normally go together, but trailhead, trail tail. We'll see if I can come up with a naming, how I resolve that little naming quirk. Okay. And by the way, looking at the states here, whenever we start the position, it needs to be in the ready state, it looks like. And then it transitions to the moving state. When we do a position delta, we expect it to go from moving state to another moving state. And when we say stop, if it can be in several states. If it was moving, then we set it to the stopping state. And then whenever it's in stopping, including if we just set it to stopping. Okay, so it's like we're letting the oldest points of the trail are still dying out, but new points aren't getting written in. So up here, a new point gets written in, and the trail end is incrementing by 1 each time as well, because, it's always 1 after the head. So if the head increments by 1, the end increments by 1. Here, the end is incrementing by 1, but the head is sitting still. So that's how we get this effect that you can see, like, when the particles... I don't know if you can see this, but when the particles like hit the center here, the trail fades away by shrinking. It's like the head is smearing out a line, and the head disappears instantly, but the trail fades out with the oldest points fading out first, and the most recently carved out spots on the trail fading out last. So the trail end is incrementing, and when the trail end gets to the head, then the whole trail is empty. The particle is now completely dead. It doesn't have any visual appearance, and so we mark it as ready. All right, now how do we draw this thing? One trail count. So this looks like it's just going to loop over all of the... So each pair of points in the trail creates a segment, Yeah, Kashanks, exactly. I know it's probably real rough over the video compression. It looks real cool in person, but when I made a video out of it, I was like, live render looks so much better than the video compressed version. I never consider that. I like making these cool effects, but I never take a look at what they look like after they go through video compression. I don't know what I need to learn to like get the. Maybe I need to learn more about codecs, or maybe I just need to stop making effects with all these little particles that don't translate over at all. Also, welcome. Okay, so we go across these segments, and right now it's all just this. We grab the pair of points. We are trying to figure out. Yeah, we end up making a trapezoid shape. So the trapezoid connects those 2 points, plus it creates sort of a radius for each one. That makes sense. Is this making sense, right? For every pair of points, for every neighboring pair of points in the trail, we want to connect them. And it's not by a thin line, it's by like a rectangle. But we want the rectangle to be a little bit, like, we want the trail to be able to get to, like, taper off. So when we connect 2 points, these 2 points are not that spread out. They're a few pixels apart from each other usually, right? There's like, if the point is moving, 3 pixels per frame, then there's 3 pixels between these 2 spots, so they're real close together, and then we have a slight difference in the width. So over the course of like 10 frames, over the course of 10 segments, those trapezoids can kind of create that tapering off effect. And so to create the trapezoid, what we do is we choose a radius value for, we choose a radius value for both ends. Each point, each of those 2 points gets its own radius. And then we are looking at the lines perpendicular, right? So we shoot lines out perpendicular from the segment. So we have some segment, and we shoot lines out perpendicular. We set the radius of each side independently, and then that creates a trapezoid. That gives us 4 points. That connect the 2 segments. And I'm realizing that that's kind of funny. It means if there's a sharp bend, right? If I go from this point to that point, and then from this point down here, right? If I have a really sharp bend, the 2 trapezoids wouldn't actually close each other. What I would actually want is for it not to have a trapezoid, but a quad where the angle, the direction of the whiskers coming out of the point is not based on what is perpendicular to the segment. I would actually want it to bisect the angle to the 2 neighboring points. So we can improve the quality probably by swapping out the trapezoid thing here. And all right, let's start making a to-do list. We are finding a to-do. Okay. Right here we take, so those are the 4 points, right? By here we've calculated our 4 points, and then we create 2 triangles out of those 4 points, setting their colors based on the 2 colors of the 2 points, right? That way we can, in addition to tapering off the shape, we can taper off the color. We can make a color gradient across the trail. Okay. So I think the other thing that is occurring to me as I was going through this is that, like, the particle itself is this data structure here. What I'm actually using here, I don't use the state of the particle. I don't use the p-value, right? So part p does not appear. Part trail count does. Part trail head and end. Okay, so it's just the trail stuff. And what's really happening here is we're sending down a sequence of points to make a trail. So why don't we start with that? That'll be our first big to do, is isolate draw from particle data structure. I'm going to just make this super generic draw thing instead of a thing that tied in with the data structure, because then I can make, because this is also the most complicated piece here. If I do that, then I can start to imagine, you know, these things together. This spans like what? 50 lines of code, and this spans almost like 90, maybe 80 lines of code. So this is the significant chunk. If this were isolated from the data structure, then I think that changing the data structure would be simpler. So let's do trail draw, right? And why is this taking an arena, by the way? Oh, right, because it's using the arena to push onto the geo list, right? Because that's how you do draws here. Okay, cool. So we use that arena and that geo list. And then, why is it taking a hue? Hue is a parameter because, right, so we're interpolating. So the rules for okay, let's also look at that in a sec. So we want to have the parameters for interpolating the trail not be static to the whole program, but to have them be passed down to the trail draw here. So the trail itself, we're going to make it into two parts, right? So you can submit two blocks here. That way, if I, you know, because we're seeing here, like, I've got trail head, trail end, trail count, all of that. And there's all this looping happening through a single buffer here. We're directly indexing into trail here and here and then doing the looping. What we'll do instead is we'll just say, like, hey, we're thinking of this as we're drawing one trail, and we know you want to submit that as either one or two arrays of points. And the reason you might want to do it as two arrays of points is because if you're doing like a loop buffer, if you're doing a circular buffer, then that way you can submit the two halves of the circular buffer in flipped order, right? So that'll be how you submit the trail itself. And then we're going to need something like the parameters for the trail. And so I'll stick this right here. And now what we want to do is figure out what our parameter trails, or the trail parameters are. The trail parameters, well, hue is going to be one of them. This min r, max r. Also, you know, I'm thinking we want a max C right here. So when we're submitting this is the two parts. But we might also have a situation where our trails interpolation, right? So when we look at this here, we're using I as a way to figure out how much to interpolate. And so we want to be able to say, okay, you know, if if the trail is fading away, then it might be a trail that used to have 20 segments, but it only has 7 now. But we still want you to interpolate those 7 as if there were 20 to begin with, right? So this is the maximum count. It has to be greater than or equal to these two. And as long as the trail isn't fading away, it will be equal to the sum of these. But once it's fading away, it will be larger than the sum of these. Okay, now the parameters give us the hue, all right, so what I'm going to do, this is going to be called trail draw params instead of trail params. This is going to be the trail itself. Oops, all right, sorry about that. Okay, and then so we'll place min and max with tail and head, because while they say min and max, in theory you could actually swap these and make this the bigger one and this the smaller one. There's no reason that has to be this way. You know, you might want your saturation to increase or your value to increase if you're, you know, a crazy person or something. So, you know, increase towards the tail, the side that's supposed to look faded away. But it's more about lining up the real purpose here. It's not about what's the smallest possible radius or smallest possible saturation. It's about it's about what location on the trail it goes to, the head or the tail of the trail. So those are the parameters there. Are there any other parameters that show up? I don't think so. Okay, so those are the parameters. Here's the trail itself. We submit it like this. So let's try to implement this again, but better. So first things first, the trail needs to actually contain something. Then we get this loop that goes over all the segments. If we only have one point, then we don't have any segments, and so nothing shows up. That seems right. Otherwise, let's see, index 0 is just going to be I now, and index 1 is going to be I plus 1. But what's going to happen is these will need to start off like this, and then we'll go index 0 is less than trail C0, then we get P0 from trail T0I. Otherwise, we get it from T1 I minus trail C0, right? And we do the same thing for P1. This should be using index 0. This should be using index 1. And then if we want to make things work better, we can. So we won't have to do both of these. We'll only do one of these each step from now on, because we could have all the zeros. On our first step, we need to calculate zeros and ones, and then from then on, we could copy the zeros into the one. We could copy the ones into the zeros, and then calculate more zeros, right? Or calculate more ones. Let's worry about how to do that optimization second. So the rest of this is going to be params, tail R, right? Things like this. Head R. Head sat. Tail sat. Tail val. Head val. Then we got our RGB. We do the trapezoid thing. If this is the last one, that can just be tested by saying index 1 equals segment count, right? Because index 1 will be one past, yeah. So if this is the last one, we put the circle down. No, that's not what we want. We want if... I guess that is what we want, actually. The only problem is that then this should actually happen. Yeah, so it's a little, some of this is a little bit off, but we can make this all look a lot better. We can fix some goofiness that's happening. For sure. Okay. So, if I did all of that right, then I should be able to swap this out with something a little simpler. When we go to draw the particle, we're going to want to set up a trail and some parameters. The parameters will just be the hue goes from the parameter there. Head R equals PRT min R max R. So this is the tail. This is sat. This is val. There's the parameters. Now, the T0 is going to be the PRT trail plus PRT trail end. C0 is going to be the trail count minus the trail end. And then if the head is less than the trail end, which is typical, that's usually going to be what happens, then T0 is going to go from the trail to the trail head inclusive. So say this is a 20 and this is 1 bigger than this, then this plus, or this minus this plus this plus 1 would give us back trail count, right? If this is 1 bigger than this, which is usually the common case, then that plus 1 is 0, and so that gives us back trail count, right? That means the sum of this and this is trail count. If trailhead is not less than trail end, then this will be the case where the whole thing is actually one. The whole ring buffer, we can represent the trail as a single contiguous buffer, not as two split ones. That'll happen every once in a while, and that is signified by this if failing, and then all of it is just contained right here, because trail end will be the beginning of the spot we want to start at, and it'll go to there. If trail end equals, okay, so this is wrong if the trail head is greater than, right, so this logic works here, but if trailhead, if our trail is shrinking, then trailhead might be larger than trail end, and then we want to do it like this, right? Yeah, okay. So there's T0, T1, C0, C1, max C we still need to fill. Max C equals trail count. Okay, so that sets up our trail. This sets up our parameters. So if I did the rewrite correct and if I've done the reduction correctly, then I should be able to go arena, geos, trail, params, trail count. Okay, so that's max. That right there is trail max C. This is params hue. Yeah, that looks the same. Okay, so the rewrite and reduction worked. Now what we want to do is we can, oh, what we didn't do is we didn't replace, no, we still have the geocircle, right? So I want to look at what are some improvements to the drawing. So this is one of them, the trapezoid thing. Improve the trail draw logic. This is one of them. Better logic for the head circle. And there's also don't compute each point twice, right? So I think we want to do it in that order, because if we stop computing each point twice, it'll be easier to fix the logic for the head circle, and then this is a little bit more interesting and tricky still. Yeah, this one is going to be tricky because it involves not just looking at a pair at a time, but looking ahead and back. Like, we have to figure out the angle for each point as we go. So So what needs to happen is we start going, and we're actually going to loop over every point. And so anytime when we're putting a 0 or a 1 after something, if it's inside the trail, that's different. That's the two buffers. But for all of these local variables, the P and the T here and so on, these are all gonna go away into just a single local version. T is this, S is this, R is this, sat is this, val is this, RGB is this, these will come back in a minute. Okay, so that's how we compute 1 point, right? And I'd actually draw one of these points. Which parts do I use? I use the radiuses, so I use these R values. I use the, I need the angle, which I haven't calculated on each point yet, and that's going to be a new tricky thing I have to do. But I don't need sat or val, I just need the RGB. What I need for each point is the radius, the RGB, and the theta, right? And the p-value, right? I use the p-values right here. So as I calculate one of these points, what I'll do is if I is greater than 0, we can actually do some draw work here. And here we'll do save previous, save to previous, right? And so what we need is v2 f32 p prev p p. We're gonna need f32 pr. v4 f32 prgb, f32 p theta, right? So here we're reading the current p out of the buffers, out of one of the two buffers. Here we are interpolating the radius and the color value. Here we need to determine theta. Now the way we were determining theta before was as an angle, the angle between the 2 points, right? It's the absolute angle. I give you 2 points, you calculate the angle between them. What we're going to do now is that will be true for the end points. Their theta will be perpendicular to the angle that runs from them to the next point over. But the interior points, so if I is greater than 0 and it is not equal to point count minus 1, right? It's not one of the endpoints. Then the theta is going to be a bisect of the 2 points left and right of it. So to calculate those, we would need a previous value and a next value. And that next value means we might have to calculate, we might be reading points twice still, which is annoying. It's fine. It's whatever. We'll figure it out. If I equals 0, then we want to... this is always annoying. So I want to know... Yeah, if point count is greater than 1, v2 f32 next point count is greater than 1, then if 1 is less than trail c0, next point equals trail t0 1, else next point equals trail t1 1 minus trail c0. Right? So that gives us our next point. And then we can use that gives us our next point, and then we're going to use the angle from delta p v2 f32 sub np minus p. Take that, and there's our theta. Right? Not quite. We want to take, this will be our theta perp, and then theta is theta perp plus 0.25f. Okay? So that calculates the theta for first point. If I plus 1 is equal to the segment count, or the point count, then this is the last point, right? So then what we're going to do is we're going to take delta p, and we also know that this is not the first point. Right. And so that lets us assume that there was a previous point. So we'll do p minus the previous point. That gives us our delta p, and there's our theta perp, and there's our theta. Interior point. Otherwise, we want to calculate next p. Like this. Except instead of using 1, we're going to use ni equals I plus 1. Ni. So there's our next point. And now what I have to do is I have to create two of these delta p's. like this. And one of them points from, so I've got an angle from the previous point to me, and I've got an angle from there to there. So I've got like something like this and something like this. If I take the average of them and then rotate it by 90 degrees, I would get my theta, right? So I think my theta becomes, right, and if I flipped the order on this, I think it would simplify to this. Theta P0 plus theta P1 times 0.5. So this is, I think, correct, although this is quite complicated, so we're going to need to thoroughly test and ensure we're happy with how this actually looks and not just shrug our shoulders if it's kind of funky. We got to really dig in there and make sure that this did the right thing. Okay, so now we're going to do PP equals P, PR equals R, PRGB equals RGB, P theta equals theta. And finally, there's the draw work. And before we were doing these trapezoids, but this is going to change a little bit now. So we're not calculating thetas, but we're still going to calculate these Q's like this. So Q0 is now the theta. Right, so R0 is PR. R1 is R. This is P theta. And this is P theta plus 0.5. This is theta. This is theta plus 0.5. This is P, this is, wait, this is P, this is PP. So the previous point, Q0 and Q1 use the previous theta and the previous R to give us these. So these are actually also the same every time. So we could go farther to not redoing calculations, right? We could avoid these trig functions here and just get Q0 and Q1 from the previous Q2, Q3 if we wanted. This might be easier if we grab scratch memory because we could create a single buffer that just contains the calculations once for a lot of these things and then run over that again, right? And so right now what I'm doing is it'll be a little easier to do this if I had a picture, but like I need pairs at a time. I need for each point, I need to ask, hey, what is this point's radius, color, and theta? And what is this point's radius, color, and theta? So I need two of those at the same time from neighbors. And so to do that without a buffer, I'm calculating that once for each point. And then after the first one, I take the previous one and the current one, and I draw something with that. So I'm getting pairs at a time, but I'm only keeping a finite amount of it around. The hard thing about that is now I'm having things like this where it's like, really, maybe it's Q0, Q1 that I want to be doing calculations for. Like I could just be calculating the geometry instead of the theta and the R, right? I guess that's what I'm thinking. Instead of keeping theta and R around each time, I could keep Q0 and Q1 around each time. I would still calculate radius and theta. Now, the other question is, how can I do theta more efficiently? And the answer for that, I think, is it's even harder to do that without pre-calculating it into a scratch buffer, because this is where I have to do this extra look ahead thing and like check if the buffer is big enough. If I were to do a calculation of just the theta at each point, I wouldn't do this one or this one inside the loop. And I'd love to get to a point where I didn't even have to do these ifs. But maybe overthinking it, not sure. Let's just stick with the current plan for now. Q0 and Q1 get calculated twice. They get calculated once here and once here on the next loop through, whatever. And we push the triangles. RGB0 means PRGB. And RGB1 means RGB. Save to previous. And then even if we only did 1 point, we will end with a geocircle at the previous point and the previous radius using the previous RGB. Alright, that's definitely buggy. I can see little notches in the trails now, here and there. So like I said, not that surprising. We might have to go and debug this very carefully to figure out what's going on. Trying to think of the best way to catch the bug. Because, like, what I could do here is just say, you know what, doing this through an animation, it's going to be kind of too much extra annoyance. So let's do this. We'll block out the draw logic, and we'll put in a new draw logic. And the new draw logic will just be to draw a trail of our own design right here, directly calling into the thing we're testing. So we can set the hue to 0. And then the question is just, can we create a trail that'll actually show the bug? That's the big question. If I succeed at showing the bug with one of my trails, then we should be good to go. T0. Array count T0. Max C equals. We'll just add those together. Remind me, what am I calling these days? T0 equals this. So we just gotta fill in some values here. So we're dealing with 1920 by 1080. So half of 1920 is 960, if I remember correctly. That's 180, 190. Yeah, 1920. Okay. 1080 is 540. So we'll grab a few of those. Let's flip the order of these so that if they don't get accidentally memory laid out and get like some kind of happy accident that it works. Now let's see. We want to move this around a little bit. So I'll have it go. We'll start off here. I'll have it grow. And then have it start to go up and down like that while it's going. Let's just see if this idea is enough to catch a bug. That won't quite do it. Let's try something a little different. Let's start with T10. Little for loop here. Ti.x equals 960 plus I times 3. Ti.y equals sine f32i divided by 10 times 5. So that should make like a little wave shape, right? And then we want to do a loop pair, split loop. Array count T0. T0i equals Ti. T1. T1. What am I missing? What am I missing? T1, I minus array count T0. There we go. All right. Let's try making it longer. Wavier. I can't quite tell if those are notches or not. Okay, those are notches, right? So now we've got a recreation of the bug that we can definitely confirm. And the question now is, can I go and debug that? Right? Let's see, what are we debugging? Do we have a debug? Guess we need a new one. Let's debug the flow effect, exe. And just because it might fail if I don't... Okay, no, it's fine. Good. F10 into that. Alright, good. Debug is up and running. Alright, let's see. So the hard part here is I'm going to have to figure out when it calculates the wrong theta, or if it's doing something wrong with the theta later, or something like that. And I don't know exactly at which point the problem is occurring, right? So let's hold on a sec. Let me see. How could I identify the correct index for that notch right there? Okay, for debug purposes, I'm going to go and modify the trail draw function to have this debug segment select I equals 0. And so when it's deciding whether or not to draw a segment, we're going to have it go if debug segment select I is greater than 0 and I equals debug segment select is equal to 0, or is equal to I. Right? And then what we'll do is we'll have main print progress get inputs graphics input key down input graphics input key space modifier flags none, then the debug variable will increment by 1. Okay, so if I start my program, it's drawing, and now I go 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59. Okay, so two things that are wrong with this. One, it should not have been possible to get to 60 without getting to the end. So somehow I'm like missing keystrokes or something sometimes. Not sure what that is. Might be because I'm not waiting for input. We could try wait for input. All right, see if that helps. But the other thing is, I'm not sure I'm actually going to be able to tell because each segment by itself looks fine. It might be the two segments next to each other aren't connecting properly, right? And in that case, what I actually need is for my debug segment select I to work like this. If debug segment select I is less than or equal to I, then we use it, right? So it'll like chop off the end and I'll be able to count that. Viper Gamings, hey, nice to see you again. How are you doing? I'm doing pretty well. All right. It's currently at 0. We go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Okay, so first of all, we're at 40. Definitely the input thing is working. So I can't just take input. If I don't wait for input, I'll drop input. It's good to know. Now, we're getting to the point where I need to figure out exactly where to stop. And I'm not going to know for sure which one is the most relevant one to look at. It's probably going to be a couple of them side by side that are relevant. But I want to figure out when I stop perceiving that notch. So we're at 40, 41, 42, 43, 44, 45, 46, 47. So it looks like if I were to look at 46, 47, and 48, I might get some hints about where the notch is coming from. Oh crap. Now that I'm taking inputs manually, Alt F4 doesn't work unless I... Okay, here we go. Boom, boom. Where is it? Flow effect, go away. If graphics input exit, input close, input, then we want to break out of the loop. Good. Okay. 46, 47, and 48 are the interesting spots. So now what we want to do is pop in over here. 682. Look right here. We want to say when I equals 46, we are interested. Boom. Okay. So let's take a look at some things here. We're looking at, this is also where if I was doing out full buffers of R values and theta values, it might actually help. Right, so PR, R, P theta, theta. Now what happened was when I eliminated 46, when I hit number 46, it still looked okay. So in I equals 46, everything is okay, or it's still, the notch was still visible, right? So I said 46, something went away. What was still visible, that is what it's still being drawn here, showed the notch. So it's possible that theta and r here are the first step of the problem. Let's look at Q2, Q3. Okay, so index becomes 47. C0, so this is not it. It's not the break between these two that caused any problem. S is that guy. The lerps, the RGB. Now we could calculate theta. Next I is 48. So next P is this one. Yep, those look good. Delta P0. Delta P1. Theta P0, theta P1. Okay. So we've got the angle from P to PP. P is at 110, 544. So it's to the left and down a little bit. Standing from P, if I look to my left and down just a little bit, I find previous P, and theta P0 is just a little bit less than 0.5. I feel like that's not what I would expect, but maybe the thetas go, probably they go counterclockwise, like they probably go clockwise like this, you know, they go the opposite of the normal graph winding direction, I suppose. What about the other one? So that one's slightly to the right and up. So if it was normal graph winding, I would expect slightly above 0. We're getting slightly below 0. So these are very close. To being 0.5 off from each other, right? If I add those together... Wait, does adding them together make sense? I'm trying to take the average angle. Is there any reason why that wouldn't work? Thought that would work. So I have like an angle right there and an angle right there. And when I add them together, the midpoint that I'm going to get is about 0.2, right? Like this is gonna roughly add up to 0.4, and then we multiply it by half, so we get 0.2. So if we have something just slightly tilted off of going straight to the left and something just slightly tilted off of going just to the right, this would give me something just slightly tilted off of going straight up. I mean, that makes sense. Let's try another approach here. Excuse me, can you stop the running program? Thank you. So if this equals 0, do the whole thing. Otherwise, if I is less than or equal to select and I plus 1 is less than or equal to debug segment select. Or segment select plus 1, right? So this will let me grab 2 segments. At first it'll show me the whole thing, then it'll show me segments. It'll show me segments 1 and 2, and remember 1 is the first segment. We don't draw anything on 0 anyways. Show me 1 and 2, and then 2 and 3, and 3 and 4, and so on and so on. And so I can find out exactly the pair that looks like it has a notch on it. So I'll only see 2 at a time. We'll see if the notch is visible that way. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46. Right there. And there. And right there. All right. I think I'm getting more confused. Actually, now it's looking like it takes 3 segments to fully wrap around the notch. Like the notch appears to have a different shape. It's like one of the segments isn't quite fully as wide as it should be. And so the 2 neighboring segments look wider by comparison, and the notch is actually one of the segments being too small. Let's look at it with 3 at a time. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, 44, 45, 46. There we go. So when I'm looking at 46, 47, and 48, those are in fact the 3 segments that make that thing look like a notch. So what I want to do is I want to take that state right there, 46, 47, 48, and I'm going to run it through render doc. So I want to see what the geometry actually looks like. So let's set this to 46 by default. Let's pull open render doc. I got it right here. Go. Capture a frame. Yeah, allow access. It doesn't matter. Render doc. Stop. Here's our capture. Wait. Probably need to rebuild first. Launch. No, don't save the capture we've got. F12 to capture. Kill it. Alright, so now, if I zoom in here. Wait a minute. Right, because I changed the counting. 45, 46, and 47. 45, 46, and 47, right? Yeah, there we go. Whoops, I didn't do a capture on that one. Launch first. Hit F12 to get a capture. Hit Alt F4 to go to the capture. And that is the notch I am talking about. That is it right there. That's the thing. So the question is, why do it look like that? And to find out, I want to look at right. Well, okay. Where are the... Okay, here it is. Draw arrays. Look at this. Do you see what I'm saying? We got these points here looking like this. And then all of a sudden, this one isn't laid out correctly. So why is it sometimes right and sometimes wrong? It must be about the axis getting flipped, right? Because if it thought that... Right, here we have a diagonal like this. And here we have a diagonal like this. So that's the problem. That's where the notches are coming from, right? I'm calculating the correct 4 points, but my triangles aren't consistently creating a strip. Whenever so this, for instance, let's take a look. It shot this way and this way to make this edge. Right, so boom, boom, boom. It shot, let's see, boom. Shot this way and this way to make this edge. So it shot up, then down. But then to make this edge over here, right, so this triangle is coming out fine. But to make this triangle, it's going to go here and then here, right? It's going to, yeah, it should have shot down and then up. But it shot up and then down, and so it makes a triangle like that. And so these were going... probably like thetas of well, BYP, what's happening here is I'm calculating a theta for each of these segments to determine its angle, and I must be getting a 50, like I must be getting a half a circle flip, like half a turn is just being added all at once. So this here is, you know, it's got a theta of like 0.4 or something like that, or maybe this is a theta of 0.54, and then this one should be a theta of 0.52, but it comes out as a theta of 0.2 or 0.02, right? 0.02, and so it's flipped 180 degrees or half a turn. And to fix that, I'm gonna need to figure out how to ensure that it's stable across the whole thing. So at least I know what it is. I don't know Let's keep this up in case I need to look at it again, but now we know what's happened. VizRob has a question about ForCoder. After building a project, the compilation window does not refresh. The exited with code only shows up after mouse movement or some keyboard press. That's strange. That's a very... That's, I mean, like... That shouldn't be happening. That's not, Yeah, if you're doing customizations, you might be missing BYP has the idea. Um, you might need to make sure you're calling the thing that does animate every once in a while. Like whenever if you're writing your own customization, make sure you're not dropping those animation calls, because that makes sure that it doesn't put the program into sleep mode at the end of a frame. I can't remember the details super well. I know that that's definitely it's not. I guess the biggest question I have is, are you doing your own customization? That's the only thing that would make sense of that to me, because that should not be happening with default behavior. If it is happening with default behavior, however, I would recommend that you head over to the ForCoder Discord, and I'll get you a link for that, because people other than me actually know ForCoder better these days. Um, uh, invite. Yeah, if it's happening with default release, it might be an operating system quirk. Like maybe you're on an operating system config. It's a little different than we've seen before or something. But yeah, here's a Discord link. Go hang out with the ForCoder Discord, and they'll be able to help you more than I can, especially here. Alrighty, so by the way, while we're taking a little breather, if you're all hanging out here and you like what I'm doing, you can support the Mr. Fourth Lab and stuff like this jam project that I'm doing today and my other projects. You can go to my blog here and read about the projects I'm working on and see the announcement video, and you can become a supporter or a member and keep this thing going. But anyways, I'm going to get back to the programming. Or maybe I'll take a lunch break. I might need to go grab a bite real quick. I am feeling... I don't know. I feel like I've got a lot of momentum, but I'm also peckish. Let me get myself a snack. I'll be back in like 2 minutes with a snack to keep me going. Thanks for bearing with me. I'm still trying to figure out the best way to light up this new spot. I definitely need some lights behind the computer. Um, but I think a light in the background maybe is not as bad as I thought. I thought it would make the contrast a problem, but having the background super dark is also kind of not great. So let's do this. Okay. By the way, hello Xcoding. Welcome. Okay, so what I wish I could do is look at the value of theta. This would be the kind of thing where it'd be cool to see if Whitebox could do this. But you know what we should do? Sometimes we do a stream. We should do a stream of checking out cool-handed projects like Whitebox and Disk Voyager and stuff like that. Something I've always wanted to do. And like right now, it'd be cool if I could see theta as an array, even if I don't want to actually rearrange the code to calculate it that way. But yeah, it looks like we need to be careful about keeping the thetas in order. So, you know what? I am just going to do that. I'm just going to manually say, we need a scratch arena. Let's just do this the easy way, you know? I don't need to burn my brain all day. Computers aren't going to get any less busted just because I'm here, unless I do something different. Let's make it easy. Let's do it right. This. PNP theta. Boom. So that's going to be pre-theta. So there's a pre-calculated theta array. There's that. This is going to be like this. We're going to calculate P and NP. Like that. And you also need PP. Which we'll get by doing U32PI equals I minus 1. NIPI NPPP. So we grab our 3 points. Calculate our theta. That goes right here. And then at the very end, If point count is greater than 0, we're going to have I equals point count minus 1. Because we didn't do the last one. We didn't do it on purpose. Because it's got a different rule from the rest. These are going to look the same if I do this. And this looks like this. Okay, so now I've calculated everything into pre-theta here. Let's see what that array looks like. That's a big leap right there. I want to double check that my logic for how I set those up makes sense. But it could be fine. See, like right there, it's a jump of 0.5, roughly, right? It's like it could have... You could take this amount and subtract 0.5 from it, and then the trend would continue. But that's like a discontinuity around the circle. And a part of what's happening here that's making this tricky is that there are, because I'm each angle, there are two different valid ways to think of the angle. And I'm calculating one of those two ways correctly, but I need to calculate it. I need to actually figure out how to get the correct one. And so anytime there's that switch, that's like, there's a jump of 0.5 from one to the other. Those are probably the notches, right? And also, it's surprising how big the jump is at the ends there. Like, I wouldn't expect it to be super continuous with, like, I wouldn't expect it to follow the same trend, but for it to jump almost, that's probably just it being off by 0.5 again, right? So I think what needs to happen is we need to think about this like a sign problem, and so we're going to be looking at something like a cross product to tell us a little bit more information about which way this thing needs to point, because we kind of want to have, like, as we're going along, we kind of want to be able to think about, like, I'm traveling along the line, the trail, and I'm sending out geometry points. I'm putting down flags on the terrain to my left and to my right. And I'm moving forward. And I want to know which way I am pointing. And then I want to angle myself a certain way. But I want to always make sure that when I pick my angle, there are two different ways I could either have left and right here, or I could put my front and back the other way around, and then my right and left get swapped. And I want to say, in addition to making sure my left and right, my hands are lined up the right way, which we're getting that part right. I want to make sure that my head is always pointed in the direction of travel. Like I should be looking towards the next point, and I should have the previous point to my back. And so the question is going to be, how can I ensure those rules are followed? I mean, there's one very expensive way to do it, which is I take this angle here, and I create a vector out of it. Not this one. I take this angle here, and I create a vector out of it. BYP says the dot product of the forward direction and back point should always be non-positive. What do you mean by the back point? I don't think that we don't have any control over what the forward and backwards points look like. The only thing we have control of is whether the forward point, the forward direction, and the whisker directions, or the perpendicular directions, are, well, we can flip the sign on the perpendicular direction. That's the thing we have control over to make it but you're right, it's dot product, not cross product, that I'm thinking of. The thing that flips sign when you flip one of the vectors. Yeah, it's too bad we don't have a co-drawing chat protocol. But I agree. If I look at, like, this is my forward direction, and if the dot product of that with the vector that shoots out at this angle maintains the same sign at every step, it should be correct. Right. Because the dot product, the way I tend to think about it is the dot product measures the degree to which two vectors point in the same direction. And so if they're pointing in opposite direction, if they're perpendicular, they go to 0. Same direction, positive. Opposite direction's negative. And so what we want here is something that, if it's perpendicular, fine. I guess the issue there is if it's perpendicular, then there are two different ways. If it's perpendicular, then there are two different ways to make a perpendicular whisker angle that would both be non-positive or non. Like I could, it's like the 0 would come out in both directions, and so you wouldn't detect a change in the twisting that way either. Based on where you're standing, you have an angle of forward motion and an angle shooting out to the side. the angle shooting out to the side, will be less than 180 degrees from the forward angle. Like the angle between the forward direct vector and the whisker vector will be less than 180 degrees, but it'll be somewhere between, it could be very close to each other, or they could be very close to 180 degrees. P is the position that we're at. NP is the next position, so the forward direction, and PP is the previous position, so the backwards direction. None of these points is the point of the perpendicular, like shooting out to the side geometry that I'm trying to create. I'm thinking, I have an idea. Let's do, instead of calculating the theta, I'm not worried about the endpoints yet. I'm going to just say, let's take the angle right, the delta angle or the delta theta, or something like that, right? So this is the difference from, this is the number of turns it takes to go from P0 to P1, from head pointed towards P0, towards PP, to head pointed towards NP. And then yeah, so that can have a sign on it that is and that will just make that an absolute value, right? And so that'll always be positive. And then I'm thinking, what if I took pre-theta here by doing theta P1 minus delta theta times half, right? So I'm always going to be taking the forward-looking direction and subtracting from it, so relative to the forward-looking direction, the amount that I want to spread out. Oh, that could be wrong. That could be wrong for a different reason. BYP, you're definitely misinterpreting the goal. NP and PP and P are all inputs, so they could be anything. We're not controlling those variables. The only thing those are inputs, and I am standing at the position P. I am looking out from P at PP and at NP. But they're all fixed points, so the dot product of those is a fixed property of the input to the problem. What I'm trying to do is create a new point. I'm trying to find an angle that bisects the angle between, from the perspective of P. If P is the origin, then there's an angle between PP and NP, right? There's the angle between them. And I want to bisect that and create the theta. Right now I'm calculating it as theta. I don't have to do it that way, but I want to bisect that. I want to create geometry that bisects that angle. So I have like a new segment. I have some radius that I'm going to shoot out from P. And the goal is to figure out the angle that I need to go to the left and to the right, or the angle that I need to use to generate points relative to P that create a segment that bisect that angle. Right? Maybe I could draw this for you, and that might make this clearer. And I can do what I've just described. The problem is getting the orientation correct on that segment so that it does not twist my triangles the wrong way. Let's take a look. Talking about I've got a series of segments, or a series of points. That make up my trail, right? And so those are inputs. And then I'm going along the way, and I'm trying to set down geometry that looks like this. Right. And the question is, like, this part is the easy part. The hard part is that, like, sometimes I'm getting triangles shaped like this. And the reason I'm getting that is because somewhere along the way, this is like, you know, we're using this point, we're using this point, we're using this point, and then it flips to using this point, this point, this point, and then it flips, right? Anytime it flips sides, we get the problem. So what I want to do is I want to say, okay, what's the angle standing right here? Let me label these. I'm going to just do pictures. I think that we've gone far enough trying to do this in our head. So we have P here, we have PP here, we have NP here, right? And what we're trying to do is we're trying to figure out where this point and this point are. And we're currently thinking of this as a matter of calculating the angle, right? So we calculate a theta, and that theta is like, it has nothing to do with this white line. It's the theta that is like this, right? We're trying to calculate that theta there. Because if we can calculate that theta, then we can use polar coordinates to use our rate. We want to combine that with the interpolated radius of our line to put down that point. The trick is, how do we prevent it from flipping like this randomly? And not randomly, but out of our control. How do we constrain our way of calculating this so that it doesn't change the winding? And I'm thinking that what we have to do is something like thinking about standing at this point here, looking forward to this position. What is yeah, BYP. So we could calculate this as a point, right, as a vector, and calculate the cross product between these two. And if the sign changes, then we flip our theta. We give it a half turn. That's what I was thinking is the obvious approach. It might not be the efficient approach, but we could at least make it correct. This is the AX BY minus AYBX calculation that we would have to make consistent, or we would have to make the sign of that consistent. So let me think. Here, okay, right, so that would be, let's just focus on, I think if I solve the 3-point version, then I can extend, I can reduce the 2-point version, the endpoints down to the same thing. The 3-point version is Yeah, my brain keeps looking for a way to calculate this without having to go from the delta vectors down to thetas. Because if I could do it all in vector land, you can usually make these things, like, you don't have to go through the polar coordinates in and back out. Like, right now I'm doing, look at a vector, convert it into an angle, do some work in angle space, and then convert back to vectors. And those conversions are highly costly. So what my brain is thinking is, like, what if you stayed in vector space? And, like, the first idea that comes to mind is, what if I normalized each of the delta vectors here, and then took the midpoint between them, and if that midpoint hits the center, then we have a straight line here. All we have to do is rotate one of the delta vectors. But otherwise, we take that new midpoint and we normalize it again. Let me check the shader toy thing, BYP. I was trying to think this through, see how much of it I understand myself, but I'll take a look at what you got. So BYP sent us this. It's there. What are we looking at here? This is cool. I don't know. I don't get it though. Blend, segment, circle, intersect, F. Solve what? We have static vars. Okay. Is there something I'm missing here? RGB. I don't. I see. Well, that's a little different from what I'm doing, but let me see if it gets the main same idea. The A, B, and C are 3 points. I see. We're controlling C with the mouse position. Okay. I'm afraid I just, like, there's not enough mapping. Like, I can't tell what's doing what here. Like, there's not enough explanation. I wish this came with section point of interest. Solve. Like, I don't even know where it's calculating the intersection point still. Where's the green? Like, I can't. Are we? Yeah, we're doing this block. Solve. Can I actually use the search? Solve. Okay, solve 3. External triangle. It's very cryptic feeling. Like, is this... So they're all running all the time. Presumably these are 4 cases, and one of them is relevant at any given moment, but... External triangle. This must be case 1. When that becomes a... How it puts this green circle down, I'm still not seeing. This is a lot. I also don't see that this is doing anything to maintain consistency. Like, you see, it's giving me the intersection point, but what good is that going to do me? You know, this is... It's switching sides. That's the opposite of what I want. I really don't care about the intersection point. What I care about is both of these points, but keeping the winding consistent, you know? I want this point and the spot opposite to it. But even if I'm over here, I want to calculate this point, right? It's like I want to do something slightly different. Yeah, I'm not sure if you can explain more what part you think that does the thing. I guess this coloring scheme must be telling me which solve is relevant, but I don't know the mapping. I don't see the mapping from color scheme to solves. What is HS? So this is our two-dimensional cross product. Inner F. B minus A, B minus C. Yeah, I'm afraid this is too cryptic for me. Like, this is too far away from language I know to figure it out from here. I'm sure that it has stuff in it that I can learn, but, like, it's not doing a lot to help me learn. under the conditions. Just like, I don't know. I like here it's running solve 1. Well, it's running all of them, so I still don't see the part where I still, like, all of this, I don't know how to map this to what I'm seeing, but like somehow ANCN ATCT intersect AIATCI CT. So you're making 2 different line segments here and finding the intersection, I assume. How do you make... I don't know. There's too many steps here that are not being spelled out for me to pick up what this is putting down. That's all right. We'll figure out what's going on another way. So the simplest idea I have is to take the unit vector, to normalize these 2 vectors, and to take the midpoint, normalize that. And if it happens to hit 0, 0, then to take this and rotate it manually into position by doing a 90-degree rotation, which is easy enough to do. And if it does anything other than hitting this point, then the midpoint between them should bisect the angle. And then when we normalize it, we can multiply by the radius. And then the only question is, like, what do we do about the fact that half the time we get one on the wrong side, right? So this here, like, I drew the yellow circles in a certain way that are just wrong. The algorithm I just described would give me this point, and it would give me this point, which would be wrong. In order to keep the winding consistent, I would want to then take cross products between this and flip the signs on my midpoint if the cross product is non-positive or something like that. Let me try it. So first things first, I'm doing this with thetas right now. Let's try calculating Q's instead. So if I have the thing that goes from P to NP, then I'm going to swap if X is, I want it on my left. So if I'm looking this way, X is positive, Y is 0. I want Y to become negative and X to become 0. And then I want Q of I to equal, do I have a V2F32 norm? I don't think I do. I think my base layer has like length. So let's just add in V2F32 norm. Okay. Grab our orientation. If the orientation is less than 0, we will make midpoint.x and midpoint.y flip around. And then finally unit vector of midpoint. But we also want to have special case So there's the case where we're doing it that way. Here's the case where we're doing it this way. We go midpoint, or we go qi equals v2f32. Direction towards np dot y minus dir np dot x. Okay. Now for the final one, it's going to look a lot like the first one this time. Except we're going to do p minus pp instead of np minus p, so that we get a angle, or we get a vector in the desired direction. We're going to rotate it the same way though, and then make it a unit vector. So these aren't q values, these are unit q values. Unit q, unit q. Now let's see if that works. And the way we'll find out unit q. The way we'll find out if that works is when we come in here, to calculate these, we'll have to go unit q I minus 1 right. We can actually get away with doing it like this, and then we'll do q0 equals v2f32 scalar mul previous radius q0 negative previous radius q1. q2 is current radius on q2, negative radius on q3. I don't see the notch. Let's turn off the debug selector. That looks pretty smooth. We still put the circle on at the end. Okay, cool, cool. I guess we can take this out now. Good on that front. And we can take this out. Good on that front. Take these back out. And then just for fun, because we kept it around, let's look at render doc, launch, no, don't save the capture, capture, kill, mesh viewer, going in here, draw arrays, and there it is. Wish I could figure out how to move back and forth. Oh, I don't get these controls, but that's okay. There we go. No orientation changing as it curves back and forth. Boom, 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 boom. And then at the end there, it puts down the circle. Brilliant. Let's see what you're saying. I can avoid the branch by accounting for the order. Let's see. Where is there a branch that you're... Unit Q... This one right here I can account for? Let me think. How will I do this? No branching. Dir PP, dir NP. Those are symmetric. That's symmetrical. This is symmetrical. So this could be flipped. So you're saying if I had them all flowing the same direction, how would that work? Let me think. If they, so you're saying instead of, because I have a unit vector pointed from P to NP and a unit vector pointed from P to PP. You're saying take that second one, the one that goes from P to PP, and flip it. Take perp of V1, V2, normalize. Add and renormalize. Well, I am noticing that I don't need to do this. Right, because while this gives me the real midpoint, I end up normalizing the midpoint at the end anyways. So the scale of the midpoint doesn't matter. Right. So if I take what you're saying and I do these both point along the direction, so boom, boom. You're saying take both of them perpendicular first? Take the perpendicular of both of them, add those together, and then normalize. Well, I still have to... Okay, I think what you're saying is this. P and P, dir, perp, PP equals dir pp dot y, dir pp dot x, negative pp np, perp pp, perp np, and then we won't need orientation you're claiming. We'll just normalize the midpoint. That does work. I don't entirely understand why that works. Let me pull up Milton to help me. So the idea comes from BYP. So thank you. But I need to know how it works. So you're right. Why does that look fine? Right? Kind of weird. Probably just an artifact of the particular shape I've got. But, yeah. There we go. That's definitely right. Okay. So we have PP pointing towards P, which points towards NP. So we end up with a vector like this, and a vector like this. And when we add those together, we end up right here. But of course, if I rotate them both by 90 degrees this way, this will end up 90 degrees up like this. So I do that rotation first. Well, couldn't I do the rotation after too? Is there some reason why I do the rotation first? Couldn't I just add these two together and say that gives me something sort of pointed in the direction of the sort of let's see the direction with that goes up over that cancels out, so it's like the midpoint between those two spots would be this guy. If I had the one I originally was doing, it's this arrow here, and the midpoint would be this guy. And we're saying that this is a 180 degree difference. I guess you're saying that this here is always a 90 degree angle. The midpoint between that and that. If I have a 180 degree difference, forget the midpoints for a second. If I look at that versus that, the midpoint, the bisector of this is like this guy, right? The bisector of this is like this guy, and you're saying that this would always be a 90 degree angle. Let me just think that through. Geometry is not my strong point. We're gonna learn a little bit here. So this whole thing adds up to 180 degrees. So this is like alpha, alpha, beta, beta. Half a turn. So alpha plus beta must always be 0.25. Yeah, I get it. Right, so here's the thing, is like if I have these four angles here, right? I've got the original angle here, I've got the original angle here, right? and I have the 180-degree version of it here. Then I look at the bisectors for both of those parts. Then I get 2 equal parts here, alpha alpha, 2 equal parts here, beta beta. That adds up to half a turn. So if I multiply both sides of that equation by 1/2, I find out that alpha plus beta is always a quarter of a turn. Okay, it makes sense. So the easy thing to do, you're saying, is we take those, the directions, we do dir pp, dir np, and then we have a midpoint. Those have been normalized, so we get the bisect point instead of midpoint. Midpoint becomes bisect point. No need for an orientation check because the orientation of this is now always going to be, well, can't. It's a little confusing to me why this fixes the problem when other things didn't, except I guess that's just the nature of taking the angle with a tangent. You have to make a decision orientation somehow that you don't make here. I just don't see it somehow. But anyway, so you take that bisect point. Bisect dir is the unit of the bisect point, and then you rotate that. And we end up like this. Now what I can do to simplify some stuff here is we're going to actually do all of this in one loop now. We're just going to say if I equals 0, or if I does not equal 0, we do this. But if I does equal 0, then PP is just going to be what you get when you do right, we just do this like this. This is going to be if I plus 1 is less than point count. We can do this one. So that should make it easier. All right. So now the next big thing is I'm putting in all this work to grab 3 points at each iteration. What if I didn't have to work so hard? So what if we start off with v2 f32 pp equals 0. And instead of all this, we're just going to go update prev pp equals p. Okay, so that gets us down by 1. But what if what if we want to get down by 2? So we'll have P come out like this, and we'll say Yeah, we'll say you calculate P U32I equals 0 like that. And then NP equals P, or P equals NP, right? So then at each stage you're grabbing NP, which is the next spot, except on the very last one you won't get anything for that. You calculate these fresh every time. This is the same. Yeah, this becomes this every time. So instead of this, we'll just start off with delta P being 0 and delta PP coming from delta NP. Similarly with dir. But on the first one, dir PP is going to need to get calculated manually. But after that, we can just do delta PP. So we really just need dir PP, not delta PP. P minus PP, delta PP. On that one, we ignore that and grab this, calculate the dir. That one, we do this, we get the dir. From then on, the dir from the previous iteration becomes the dir PP. And so delta PP doesn't actually need to get calculated at all there. All that needs to happen is dir PP needs to become this. Oh, but we do need, on one occasion, we need delta PP. That's right here. See how we're doing so far. This can be delta NP. So kind of what we can do is we just say we calculate a new dir NP, but if I equals 0, we need to do this. If I plus 1 is if we're on the last one, then dir NP is just going to be dir PP from last time. So the first time through, dir PP is invalid and we have to calculate it this way. The last time through, these don't do us any good, and we just ignore them and do this. But we want to not, well, okay. So one step at a time here. If we're on the last step, then we just grab NP that way and we're done. Otherwise, we will calculate these, and if we're on the first step, use that to fill in dir pp. And the only thing we have to do is these need to be, this needs to be declared ahead of time so that it can come from either path. Okay. That can just come from that. This can live out here. Here's how we calculate NP. We either grab it from the last step on the last step we grab it from here. Any other time we subtract and take the unit vector. On the first step we correct dir pp by doing this, and then we go boom. There we go. All right, so that's pretty good for drawing the trail. Now if I come down here and kill off the test case and re-enable the original logic, I get this. This is fine, except it's way slower than it used to be. I'm not sure why. I mean, it might be that the calculations we are doing now are much more expensive. I was doing like a couple of trig functions, like a couple of polar functions per segment before. You know what? I might still be doing a bunch of trig functions in addition to everything else. Let me look at that part. Trail draw. So I'm pre-calculating all the Q values. And yeah, I still have this like P theta thing, read P from trail. What are we doing with P? Are we doing anything with P at this point? Yes, we do something with P. Let's take a look at what it is. Delta P theta, determine theta. I don't think we need to determine theta. I think if we stop determining theta, everything will still work. But we still need the P values because we're doing stuff relative to those P values. So we keep that in. We don't care about P thetas. All right. We don't care about this. Still crazy slow compared to the way it was before. All right, where are we hitting a problem? These are all real trivial. Q, P, 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 dir, P, P, I, dir, delta, unit. So we're taking a unit vector once for each twice. 1, 2 times for each point. And we're doing 1 pow. We were doing that already. How could this be so much slower? That's the thing I don't get, because it was running fine before. I guess I'm gonna have to start profiling it. I'm gonna have to wrap up for the day. In a minute here. But like right up until I switched from the old way of drawing trails to the new way, it was perfectly performant. So I don't know. I don't know why, like, nothing has changed except maybe that I had render document. I don't see how that would matter. I don't know if it's the graphics part, but like I haven't changed the number of triangles that are being sent. So it feels like it has to be all of the, Oh! I know what the problem is. There we go. Now it's running at full speed. Not a performance problem at all, just a bug. Animation bug. Alright, so it all looks basically the same, maybe slightly smoother than it did before, although probably doesn't make any difference once the video compression has its way with it. But the progress here is good. What I need to do coming up next is yeah, we did this. Yeah, okay, so we did all of this for today. So my next big steps are going to be, now that I've refactored the trail draw part, I want to improve the API for the particle updates. And then set up the diffeq flow calculations, of course. Hey, thanks, man. Thanks for the nice comment. By the way, if you're hanging out and you like this stream or you like any of the stuff I do, remember to go check out mrforth.com/membership. You can become a supporter or a member. There are cool perks. And you help me keep this kind of project coming. You can go over to my blog and read more details about this system as well. Check out the announcement video where the flow effect was first featured, but again, with video compression. Some people like to do these discounted yearly versions, by the way. It's a cool option too. Anyways, thanks for coming and hanging out on the stream today. Expect another couple of hours of this tomorrow where we'll get to a little bit more of this. And, you know, I'll add another to-do actually. Now that I know I was just in the middle of wrap up, another to-do popped in my head. Strip out the animation, the special animation control stuff. Anyways, like I was saying, thanks for coming to hang out at the stream, and I'll see y'all around here tomorrow around the same time, maybe a little earlier or later, but probably about the same time. And yeah, see you around.